I'm going to take you through an ANOVA example to illustrate how it works after describing some of the theory. So here is some data about plants that are propagated through tissue culture and weaned on different composts. So the composts are just called A to B. They're a plant type lobelia called Hannah, and after 8 weeks the plant weights were recorded. So what you've got is the mean weight of A, B, C and D. You've got their variances, the S squared. You've got the sum of the x's, the sum of the squares of x's, and the number in each group, which is 10. So this is going to explain why you don't want to do these by hand. So the first thing you need to do is get the sum of the x's of all of them together, the sum of the x squareds of all of them together, the sum of the x squared over the size of each of the different groups, and then the sum of the x in total divided by the total number. Then, once you've done that, then you can calculate the sum of the squares of the total, the sum of the squares between, and the sum of the squares within. So, sum of the squares between the groups, sum of the squares within the groups, and the sum of the squares in total. Then you put that into what's called an ANOVA table. So there you've got your sum of the squares between composts, sum of the squares within composts, and the sum of total variation, the total sum of the squares. Beside that, you've got your degrees of freedom. There are 4 groups, therefore it's 4 minus 1 to give you degrees of freedom, which is 3. There are 40 plants across the 4 groups. Take away 1 for each of the different groups. That gives you 36 degrees of freedom within the composts. So you then look at the variation you've got. So the variation within is 56. So you divide that 56 across the 36 different plants. So the variation of each individual one is 1.5. You divide the variation between the groups, which is 26, across the 3 different degrees of freedom between the groups, which is 8.95854. So in the end, your F calculated is this 8.9584 divided by 1.56, which gives you an F statistic of 5.75509. Now the critical value for a p-value of 0.05 with 3 degrees of freedom for V1 and 36 for V2 is 2.872. So the F calculated is a lot larger than the critical value, so you can reject the null hypothesis that there is no difference between the different groups at the 0.05 level. There's actually a very highly significant difference between the different groups. However, the only thing this has told us in the F test is that there's a difference between the 4 different groups. It's not told us what the actual differences are, which to my mind is not very useful. So doing it by calculation is complicated. By hand, I've seen very few people manage to do one of these questions correctly. It's just tricky. Doing it in SPSS is a lot easier. So what you want to do is put all your response variables in one column. So in this case, all the weights in one column, and the second column needs to be your grouping variables. In this case, your compost names A to D, but you need to, in SPSS, replace them with numbers. So in this case, it becomes 1 to 4. The reason you need to do that is because SPSS now doesn't allow you to have character names for your different grouping variables in ANOVA. It's because it wants to do a plot of them. And so I said that they're a combination of both t-tests and regression methods. So what it's doing is fitting a line for all the 4 different groups. And what you're doing is, if they all have the same mean, you'll get a horizontal line. If you get any deviations from the horizontal, then they do not share the same means. Right, so in SPSS you go to Analyze, go to Compare Means, go to One-Way ANOVA. Weight is the dependent variable, compost is the factor, and you select Post Hoc, which allows you to do t-tests. You then have to click on a selection correction criteria to deal with, you're not doing one t-test, you're doing many different t-tests. So usually we click on something called Bonferroni, and that makes sure that it deals with multiple test correcting, which we'll come to in a second. SPSS will then give you this ANOVA table, which you can see is exactly the same as the one that you got by doing it by hand. So what you've got is your sum of squares for the between, within and total. You've got your degrees of freedoms, 3, 36 and 39. Your mean squared difference is 8.959, 1.557, and your F statistic of 5.755, and its significance is actually 0.003. The second table it will give you is this. So these are the t-tests between pairs of groups. So you've got compost 1 against 2, 3 and 4, compost 2 against 1, 3 and 4, compost 3 against 1, 2 and 4, compost 4 against 1, 2 and 3. You've got their mean differences, their standard error, their differences, the confidence interval for their differences. The thing that you're looking for is the sig column, which tells you their p-value. So there's a significant difference between compost 1 and 2, not between 1 and 3, and also between 1 and 4. You can see this in the confidence interval for the difference. So for the first one, it goes from 0.5 to 3.6, always positive. For 1 and 4, it's between 0.3 and 3.5, also positive. But between 1 and 3, it goes between minus 0.46 and plus 2.65. So that includes 0. It includes no actual difference between the two. And then you can look at 2 is significant difference with 1, no difference with 3 or 4. 3 is not difference to any of the others, and 4 is only difference to compost 1. However, if I'd have done the box plot, I could have already seen which was going to be the differences between the composts. This is why box plots are very useful to do before you carry out ANOVA. It allows you to see what is the most likely difference and to interpret the meaning of your F statistic.